So welcome to lecture 7.2 of the group theory course. This is the second lecture of chapter 7, and in which we discuss the applications of group theory to the electronic states of molecules. And today we are going to extend what we did last time and discuss the electronic structure of multi-atomic molecules and three-dimensional molecules. And this lecture is going to be arranged as a sequence of several examples. And we will start with the first one, which is the ammonia molecule, the NH3 molecule. I show here both the geometry of NH3 and also its electronic structure. So there is a nitrogen atom bonded to 3 hydrogen atoms. Hydrogen atoms have 1s orbitals, and nitrogen has s and p orbitals, so it can make several bonds. And also it has 5 electrons. So what we are going to see actually in the end is that the best way to describe the electronic structure of NH3 is to start from a hybridization of the nitrogen atomic orbitals in an Sp3 basis. So in this way, then I can make 4 Sp3 orbitals, and I can make what we called last time direct valence, that is sigma bonding orbitals between nitrogen and hydrogen. And since nitrogen has 5 electrons, then I can use 3 electrons of nitrogen to make covalent bonds here, and I have 2 extra electrons that actually become a lone pair state in this Sp3 like vertical orbital here. So let's see how this works in terms of group theory. So this is I have already described for you. This is the electronic configuration of nitrogen and hydrogen. We ignore the 1s state of nitrogen, and we will deal with only the 2s and 2p electrons. And this geometry is suggested of Sp3 hybridization. And so a reminder of what Sp3 hybridization is, as I mentioned, I can make a linear combination of s and different types of p orbitals, like consider the 3 px, py, and pz orbitals, and I can start from these 4 different orbitals and make linear combinations of them and construct another set of 4 orbitals that we called Sp3 orbitals, Sp3 hybrids. We're going to see this in more detail when we discuss today the methane molecule, CH4. Okay, but the same idea applies here to nitrogen. Sorry, to ammonia. Okay. So let's start the analysis from the group theory point of view. From the group theory point of view, this is a C3V symmetry, the point group C3V. Remember that although this is looks like a planar molecule, but the molecule is not planar. This is just a projection. So because the nitrogen is out of plane, so you have to remember that. And that's the reason why you have only C3V symmetries. The only symmetries you have are the identity, the 2 C3 operations, and the 3 sigma V reflection operations. Okay, and this is the well-known character table of the C3V group. And following the steps that we described last time, we start from by constructing the equivalence representations and the characters of the equivalence representations, the atomic size characters. And to do that, we just have to count how many. Okay, so we initially we are starting just to consider the s orbitals in the hydrogens. Okay, this is important. We are going to deal with the nitrogen later. Okay, if you ignore the nitrogen for a while and consider only the hydrogen atoms, and then the chi-as atomic size characters. You remember you have to count how many atoms remain unchanged when you apply the different symmetry operations. So the identity, you don't change any of the hydrogen atoms. For the C3 you change all of them, so the character is 0. And for the reflection, the vertical reflections, one atom remains invariant. So this, for instance, for this reflection plane, this atom does not move. So we have a character of 1 here. And this is a reducible representation, and we have learned already how to reduce it into IREPs, into irreducible representations of the group. And this is a simple case. Actually, we have done that before. And in this case, we can see that this decomposes into gamma 1, which is also A1. This is another notation, and gamma 2, which is the same as A1 plus E. Okay. All right. We have done this many times already now. Okay, so we have actually done this problem when I think in chapter 4, when we considered the equilateral triangle, the s orbitals in an equilateral triangle. So what I'm going to do is just reproduce here the results we have already obtained. So the idea is that if we want to find basis functions as linear combinations of these hydrogen s orbitals with these specific symmetries, this is the exercise we have done already. So, and the result I'm going to reproduce here. If you take the A1 representation, is the symmetric sum of the s orbitals in the atom 1 plus the s orbital in the atom 2 plus the s orbital in the atom 3. So I can arbitrarily choose this as the atom 1, 2, and 3 here. Okay. And for the two-dimensional representation, then we have two different partners. The first partner for the gamma 2 or A2 representation, let me call it gamma 1, let me call it A1, and E, let me call it E. So for the E representation, I have two partners. The first partner we'll call 1. Then I have, if you remember, this linear combination with complex coefficients. In which omega is e to the I 2 pi over 3. And the second partner of this representation, E2, it's equal to a similar kind of linear combination, but going on the other way around of the triangle. Okay, so we discussed this last time. This means that in one case I add phase factors of omega going around one way, and in the other case I add phase factors of omega going around the other way. So, or if you want, e to the I 2 pi over 3 going this way, or e to the I 4 pi over 3 going this way. It's the same idea. All right. Okay, so this we have seen before. So remember that these are complex numbers. So it's interesting to visualize these complex numbers in the complex plane, and this is going to be useful in a minute when we discuss an hexagonal molecule. So this is I'm making linear combinations of 1 omega, which is this vector here in the complex plane, and omega square, which is this vector here in the complex plane. So these are the coefficients that I get. Okay. So what's interesting now is that I can make this is the E state is a doubly degenerate state, right? So these two wave functions are wave functions of a degenerate state, and I'm free to make any linear combination of those that I want. So for the purpose of today's analysis, it's interesting to make the following linear combination. Let's say I make the sum and the difference between the two. If I sum E1 and E2, I'm not worried too much about normalization here. But if I sum the two, you see that I get 2s1, and you notice that omega from the complex plane, notice that omega plus omega square is actually -1, right? So this is 2s1 minus s2 minus s3. So it becomes a real function, a function expansion with real coefficients. Okay, and I can make the difference now. If I take the difference E1 minus E2, I get so if I subtract these two numbers, it gives me I. So this is a constant I, imaginary number, and I don't worry too much about this constant, but this is S2 minus S3. So this is interesting when I make this linear combination in terms of real numbers. So I forget about this I is a constant that I can ignore. So I can visualize these wave functions in the following way. So the first one, the A1 representation, is easy because it's just a symmetric sum of the three s orbitals. But let's see these 2D basis functions here. 2s1 minus s2 minus s3. So this is atom 1, right? And so a wave function with larger probability and positive here, and the smaller probability and negative here. So I will use this notation to indicate the sign. Okay, when it's red, then it's negative. When it's open symbol, then it's a positive. Okay, so this is the state E1 plus E2, and the state E1 minus E2 is S2 minus S3. So it has a node here. So the probability of finding the electron in the atom 1 is 0. So this is 0. We'll symbolize it as a small dot. And it has different signs for it's positive for S2 and negative is positive for S2 and negative for S3. Okay, so this is an interesting way to draw the wave functions as a combination of s orbitals in this molecule. Okay, these are the wave functions I get. Is it clear? Okay, so very good. So now this is the hydrogen atoms only. So to make the covalent bonds, now I have to consider the nitrogen orbital. So I have to see what combination of nitrogen orbitals will couple, or what linear combinations will make bonding and anti-bonding states with the A1 and E symmetries of the hydrogen states. So only combinations with the same symmetry I can use to construct molecular orbitals. Okay, and that's the idea. So in this diagram, this is explained. And let me go through. There's a lot of information here, so let's go through that step by step. Again, this is the hydrogen basis orbitals that I have considered. I start from 3 1s states, and I make two types of linear combinations: the totally symmetric A1 symmetry, which is this linear combination, and the two partners of the E double degenerate IRAP. So this is one partner, this is the other partner. This is 2s1 minus s2 minus s3, and this is simply s2 minus s3. Okay? All right. And now let's consider the nitrogen atom, and as I proposed, let's start from the hybrids. Let's start from the 4 Sp3 hybrid states. Okay, so these are the 4 orbitals, and I need to make linear combinations of the same symmetry as the hydrogen atom. So, and you can see that if I make if I consider these 3 Sp3 orbitals with equal amplitude on the 3 of them, this is transforms as A1, and also the lone pair orbital A1 is also, the lone pair orbital also transforms like A1. Okay, and for this other Sp3 orbitals, I'm just doing here the same thing I did for the hydrogen atoms. Okay, I just applying the same symmetries, because I know already that I have to construct orbitals of the same symmetry to make bonding and anti-bonding states with the hydrogen atom. So this is just the shape of those orbitals. Okay. So, and then I start making bonding and anti-bonding states. For the A1 state, this will couple with the A1 combination of S hydrogen atom states, and this will make bonding. This is the bonding state, and anti-bonding state. So this is the anti-bonding state. Okay. What else? Then I can analyze the E states. So the E states will again have bonding and anti-bonding states. Okay. And finally, this is a doubly degenerate state. This is a doubly degenerate state. And finally, the lone pair right here. So then I start to occupy all these levels. I start to occupy these levels, and I have 5 electrons from nitrogen and 3 electrons from hydrogen. So I have a total of 8 electrons. So 1, 2 electrons here, 4 electrons here, and 2 electrons here. So as we have anticipated, the lone pair state becomes doubly occupied. Okay, and this is the HOMO, the so-called HOMO, the highest occupied molecular orbital. And this is the electronic structure of the ammonia molecule. Okay? All right. Now, let's move on and consider the CH4 molecule, the methane molecule. In this case, once again, we are going to have Sp3-like hybridization, but it's a different point group. Now, I have now the TD group, the tetrahedral group. So the tetrahedral group has more symmetry operations. It has all these different symmetry operations right here. And again, I'm going to follow the same steps. I start by considering the linear combination of s orbitals from hydrogen atoms, and I start then by looking at the equivalence representation. And when I apply the identity, atoms don't move. For C3 is a rotation around one of the CH bonds, right? So one hydrogen atoms, it's invariant, and the other 3 move. So the character is 1 here. For C2, all atoms move, and for sigma d, this is one of these planes, for instance. 2 atoms are invariant, and for S4, all atoms move. So these are the characters of the equivalence representation, the atom size representation, and you can decompose them. This is the result. It decomposes into A1, totally symmetric, and T2. T2 representation is a 3-dimensional representation, and you can see the basis set for T2 is the vector, okay? The components of the vector X, Y, Z right here. Okay. So once again, one can construct linear combination of s orbitals for the hydrogen atoms. I'm not going to do this. It's an exercise that you can do it, but I mean, since we have done that already a few times, I'm not going to do that. But I'm just going to give you an answer. But I will argue that this is a very reasonable answer, in the sense that for the totally symmetric representation A1, you could already anticipate that you have a totally symmetric sum of the four s orbitals. You can label them A, B, C, D. In an arbitrary way. Let's say, I don't know, you can call this A, B, C, D, and psi A, psi B, psi C, psi D are the s orbital wave functions centered around each one of these hydrogen atoms. Okay, so this is kind of trivial, but this is the 3 T2 basis functions, and you can see that I can start playing with the different signs here. This is A plus B minus C minus D, A minus B plus C minus D, A minus B minus C plus D. So if you look how this in the next slide, we're going to see how these wave functions look in real space, and we are going to see that it makes a lot of sense that these 3 wave functions transform like the 3 Cartesian coordinates of a vector. Okay, so what about the carbon atom? As we argued before, it's the same thing. I have to make linear combinations of A1 and T2 to couple with the linear combinations that I have constructed for the hydrogen orbitals. Okay, and this is trivial because you can look right away here. Remember, I have one s state, 2s state, right? And I know that for a carbon atom centered right here in the symmetry point, the s state transforms like A1, right? It doesn't change at all when I apply all the different symmetry operations of the group. So this is my carbon S state here, and you can guess again that the 3p states I can make linear combinations and make them px, py, pz, and they have the same transformation properties of the vector x, y, z. So this px, the orbitals px, py, and pz are also a good basis function for the T2 irreducible representation. So this is done already. So I know that the carbon S state will couple with this symmetric combination of hydrogen S states, and I know the 3 p orbitals of carbon, they have T2 symmetry, and they will couple with the 3 T2 linear combinations of hydrogen S states. Okay, very good. So here I explain why it makes a lot of sense to make those linear combinations of hydrogen molecules. So of hydrogen S orbitals. So for instance, if I call this axis my z-axis, for instance, okay, and then you can see this is positive S1, S2, and negative S3, S4. I think I'm changing my notation here. Let me call this positive. This is positive. It doesn't really matter, but this is positive. This is negative. So you can see right away that this transforms like a z component of a vector. Okay, it's positive for positive values of z and negative for negative values of z. So this will certainly couple to the pz orbital. This is the pz orbital right here, and I can use the same arguments for py and px. So these are again linear combination of s orbitals in the hydrogen atoms, and that look like this is the y-axis, right? So if this is py, and if this is px, and you can see that they transform exactly the same as these 3 linear combinations of x, y, and z. I can draw x right here, and y is a little bit harder to draw, but something around like here. Okay. So I hope now it's clear why that result is correct. I mean, why these different types of linear combinations of s orbitals, they have the same transformation properties of x, y, z components of a vector, or if you want, px, py, and pz orbitals. Okay. So, and of course, I also have the totally symmetric A1 orbital, molecular orbital, or linear combination of hydrogen molecules, or hydrogen orbitals. Sorry, so it's totally symmetric linear combination. And then I start to make covalent bond, bonding and anti-bonding states. So A1 will couple to the A1S state of carbon and make a symmetric bonding combination, this one, and the anti-symmetric bonding, anti-bonding combination, this one. And the 3 px py pz orbitals will couple bonding and anti-bonding combinations of the corresponding linear combinations of s orbitals. This is the bonding combination. This is the anti-bonding combination. So this is the molecular orbitals of methane. And you have some experimental values for the electronic energy eigenvalues. Okay. All right. So you might wonder why I started from hybrids. When I discussed the ammonia molecule, I started from Sp3 hybrids, and here, which is also sort of a tetrahedral structure, I started from s and p orbitals. So the answer to that is that it really doesn't matter, because this will give me in the end the same answer. So what I'm going to do now is do an exercise to show you that if I started from hybrids, I would get exactly the same result. Okay, so that's another possibility. Start from Sp3 hybrids, and again, when I make Sp3 hybridizations for carbon, I have these 4 Sp3 states that are easy to see that they will make bonds to the 4 neighboring hydrogen atoms. Okay, and so how can I start this discussion from these Sp3 orbitals? First, I have to make the hybrids. Okay, I have to make the hybrid atomic orbitals, and the way to make hybrids is, again, is to make a linear combination of s and p orbitals in a way that I have to point along the right way. Okay, so in this choice of coordinate axis, I can see that one of the bonds is oriented in the 1-1-1 direction. Okay, this is a very convenient description for let's say silicon or diamond crystals in which the bonds are oriented along 1-1-1 type directions. So that's probably where this came from. So the idea is that I make a linear combination of x and px, py, pz oriented along 1-1-1. Okay, px plus py plus pz gives me a p orbital which is oriented along 1-1-1. And then I do the same for the other 4 bonds. So each carbon atom makes 4 bonds. This is the same in methane or in diamond. And the direction of the other 3 bonds are just those ones. 1 minus 1 minus 1, minus 1, 1 minus 1, and minus 1 minus 1, 1. Okay? 2 coordinates negative and 1 positive coordinate in each case. So these are the different linear combinations. So these are the 4 hybrids. These are the 4 Sp3 states. If you think about it, they could be in an isolated carbon atom. They are not an eigenstate, but these are combinations with the same expectation value of the energy. Okay, because they are identical. They are equivalent to each other if I apply symmetries of the group. Now, in the TD group, I cannot have a 4-fold degenerate level. So this will have to break and into A1 plus E. And that's the idea. I have to make, once again, linear combinations of these 4 Sp3 orbitals with the same symmetries as the linear combinations of s hydrogen orbitals that I have discovered already, A1 and T2. Okay, And if you think about it, the combinations are precisely the same, because these 4 different s orbitals, they will have exactly the same symmetry properties as a whole as the 4 sp3 orbitals. They transform exactly the same. So I can already anticipate that the 4 linear combinations that I can make are essentially the same as the ones I have for the s orbitals in hydrogen, in a sense that instead of using s orbitals as psi A, psi B, psi C, psi D, I use the 4 hybrids. Okay, but the linear combinations are the same. So, and that's the idea. You can. So let's start to. This is what I have just said. Let me see how this develops. So psi A, psi B, psi C, psi D. I can call this one psi A, psi B, psi C, and psi D. And let's see what's the result of doing all these 4 different types of linear combinations. So for instance, for the A1 representation, the totally symmetric, I sum all of them, right? So what happens when I sum all these 4 wave functions? You can see that psi s, I sum all the 4 values, but for px, py, and pz, you see there's a cancellation here, right? So the result of this sum of 4 hybrids is just the s state, 2s state of carbon. Okay, and this is the same result as I have found here. I mean, I started with the s state as the one transforming according to A1. If I start from atomic orbitals S, Px, Py, Pz, but if I start from hybrids, I get the same result. Okay? And let's see this other guy right here. So this is for the T2 representations, the 3 partners. Let's see this guy right here. Psi A plus psi B minus psi D, C minus psi D. And in this case, you can see that I cancel the s orbital, right? Because, I mean, I have minus sign here, plus sign in the first 2, minus sign in the other 2. So this got canceled, and in the end you can see that Py and Pz are also cancelled, and I only have Px. So this is a Px state, and you probably can figure out that the other 2 are going to be Py and Pz. And this is the same result I got when I started from the atomic orbitals, not from hybrids. Okay, so no matter if I start from hybrids or if I start from atomic orbitals, in the end I must get the same symmetries, the same functions that transform according to different irreducible representations of the group. Okay, so let's move on. Let's consider now the hypothetical SH6 molecule. So 6 hydrogen atoms around a single sulfur atom. So this molecule actually does not exist in this form, but it's just an exercise to try to see how an hexagonal group, as an example. Okay, so and let's focus only on the hydrogen s orbitals. Let's ignore for a while what happens in the sulfur atom. So in this planar molecule, so the group is D6H. It has D6H symmetry. So we have many symmetry operations. This is the character. So this is the character table of the simpler D6 group. To get D6H, I couple D6, or I make the direct product of D6 with the sigma H, or the inversion. But it's sufficient to analyze the character table for D6, because if I think about hydrogen s orbitals, any linear combination of them is going to be even under inversion, okay? Even under sigma H. So it's sufficient to consider just this portion of the D6H group. So, and these are the symmetries operations I have. I have C2, I have C3, I have C6 operations, 2 rotations of 2 pi over 6. And I have 2 horizontal axes, C prime and C double prime. And let's construct the atom site representation. This is 6 for hydrogen atoms, right? For C2, for all rotations around the main symmetry axis, the character is 0 because all atoms are moving. For C2 prime, I have these 2 atoms right here that do not move, so the character is 2. And for C double prime, which is this guy here, the character is 0 again, right? Because all atoms move. So this is atom site characters, and this is a result of the decomposition of these reducible representation into irreducible representations. Gamma 1 plus gamma 3 plus gamma 5 plus gamma 6. So I have 2 one-dimensional representations and 2 two-dimensional representations. Okay, that's the result of this decomposition. All right, so what I should in principle do now is to find the basis functions. So this would be a longer exercise in terms of algebra. So I'm going to skip that. I'm going to just show to you how they look like, and then I will discuss and hopefully show to you that it makes a lot of sense that they look like that, based on our previous experience with the triangle. Now I have an hexagon, right? So before I had a triangle, if you remember, I was making linear combinations of s orbitals, and I would introduce different phase factors between s orbitals in different from one neighbor to the other neighbor. And I will just do the same thing right here, right, with this molecule now for the hexagon. So for the hexagon, instead of using omega only, e to the I 2 pi over 3, I can use the big omega, which is the I e to the I 2 pi over 6, the 60-degree angle phase factor. Okay, so I can play this, and you see that this makes an hexagon here, and I can just play with those phase factors. For instance, the totally symmetric representation transforming as gamma 1 should be a symmetric combination 1 1 1 1 1 1 on the coefficients. So A, B, C, D, E, F are this A, B, C, D, the different labels of the hydrogen atoms. Okay, so what else can I do? I can now introduce a phase factor of big omega. Okay, so A omega, big omega B, small omega C, because it's twice big omega, right? And so on and so forth. -1. So it's like going around the circle and introducing all these different phase factors. You can see that? This is the complex plane. You can imagine that there's an hexagon here with the different atoms I have in my different hydrogen atoms I have in my hexagon. I can try to draw this. I don't know if it's going to be very good, but this is what I'm talking about. Oops. So this is A. This is A, B, C, D, E, and F. All right, so now I can introduce a phase factor of omega between A and B, and between neighbors. Okay, so and this gives me this combination. Now I can go around the circle. Now the phase factor of -1 between neighbors. So this gives me A minus B plus C minus D, yeah, and so on and so forth. And I can go around the circle clockwise, which I just did, or I can go counterclockwise, and this is equivalent to, instead of adding a phase for instance, e to the I 2 pi over 6, I can add a phase e to the minus I 2 pi over 6, and I get a different state, right? But these two states, they should have the same energy. You can figure that out. It's like going around the circle in different directions with different phases, but having the same energy. So these are the other two possibilities. Okay, so it's reasonable to guess that psi 2 and psi 6, they should belong to the same irreducible representation, because, as I said, they are just the wave function going around one way or going around the other way, and the same for psi 3 and psi 5. And you can guess that this one, psi 1, transforms like gamma 1, and psi 4 transforms like gamma 3. These are the 1D representations. Okay. In the book, you see that you can show precisely by looking how these different states transform according to different symmetry operations of the group. You can actually certify that you can make sure that what the representations they belong to. But this is we can check that later if you want. Okay. Now, how could I guess the energy order of these different states? So, in a way, this is similar to what we do in solids when we consider Bloch states of different wave vectors. Okay, and I'm going to try to show you this analogy. So, I minimize the energy when I make bonding combinations, and I maximize the energy when I make anti-bonding combinations. So gamma 1 is clearly a bonding combination of these orbitals, because the phase is the same. If I think there is a molecular orbital here, another here, I'm just summing them with the same phase factor, 1, 1, 1 for all of them, right? So I should get a state with a small kinetic energy, because the wave function does not oscillate too much. So that's why I get the smaller energy. So this is like a constant function. If you look at the like plane, this is a periodic a Bloch state which is a plane wave times some local orbital, and in this case the plane wave is 1. It's a k equal to 0. Right? This is analogous to a wave with k equals to 0 momentum. And the anti-bonding state, gamma 3, is the opposite case. So I invert the sign, A minus B plus C minus D. So this is positive, this is negative, this is positive, this is negative. So this is the maximum kinetic energy I can get. So this is like a wave doing like this, right? With a high momentum, and therefore high kinetic energy. So, and the two intermediate cases, they are, so here we have the real imaginary part of them, but I can make linear combinations of those, of each partner, and make sine and cosine like, and if you could do that, you would see that, let's see, this guy here, the gamma 6 state, you can see gamma 6, it inverts the phase going from A to D, right? Plus A minus D. So if I make sines or cosines, this should be positive here and negative here in D, and then going positive again. Now for gamma 5, I oscillate twice. I make a complete oscillation from A to D. So this gamma 5 should go like this: positive, negative, positive, negative, so on. Okay, so you can see that the wave vector of these oscillations, it increases going this way. Okay, and that's why the kinetic energy increases for these plane waves, and that's a way to guess the energy ordering of those different states. Okay, let's do another example now. This is the octahedral SF6 molecule, X of fluorine, I think, of sulfur. And this is an interesting example because it's an octahedral field, which is very common. We have seen that already when we discussed crystal field splittings, if you remember. So this is the OH group, the cubic group OH. And I have 1 sulfur atoms in the middle, and then 6 neighboring fluorine atoms. If I consider the atom site characters, these are the equivalence representation characters for the 6 fluorine atoms. And if you do the decomposition, this will decompose into A1H, EG, and T1U. Okay, so let's see if I don't have the character table here, sorry. So I should have the character table somewhere, but don't worry too much about it. So let's so what I'm going to do in this exercise here is to assume that in each of the fluorine atoms I have s orbitals, and this is not the case in real life, because what I should have here are actually p not p electrons but p holes. Okay, but let me take a simplified case here in which I assume that I have s atoms, but in the next problem set, you're going to do the real problem. You're going to consider that I have p orbitals in each of these fluorine atoms. Okay, so but just let's assume that I have a hypothetical s orbitals in the fluorine atoms. So the question is, what are the different linear combinations of sulfur that can be constructed with the same symmetries? Okay, so we have done this many times. So the atom sites equivalence representation gives me already the linear combinations of s orbitals that I can construct. I can construct a totally symmetric A1G, a doubly degenerate EG, and a triply degenerate T1U irreducible representation. So what I want to do now, and you have to repeat that in the problem set, is to let's think about now the sulfur atom. How can the sulfur atom arrange its electrons in a way to build combinations that have precisely the same symmetries, so I can make bonding and anti-bonding states with these states here, with A1G, EG, and T1U. So let's see how it goes. So originally, sulfur has 3s2, 3p4 electronic configuration. So one could think that I should just look at s electrons and p electrons at the central sulfur atoms and how they split according to the crystal field, right? This is s electrons. These are the 3p electrons. And if you think about it, the L equals to 0 representation of the full rotation group, it splits, it's just the A1G, and the L equals to 1 is the T1U. So far I'm okay, because I can make bonding and to bonding to the A1G and to the T1U states of the the fluorine atoms. Okay, but how about the EG? How about the EG state? So to make an EG linear combination, I need to go to L equals to 2. That is, I need to go to d electrons, d orbitals. So the only way to make a bonding or anti-bonding molecular orbital with EG symmetry is that if I promote some electrons from the original S and P electronic configuration to the D shell, to the D states. Okay? And that's exactly what happens. So the system gets more stability if it makes this by making this covalent bond. So the way to do it is to promote the sulfur atom to an excited state. This is called configuration mixing. So instead of having the ground state configuration 3s2, 3p4, it promotes 2 electrons, one from S and the other from P, 2 electrons to the D orbitals. So I have 3s1, 3p3, 3d2, and this is the precise number of electrons that I need to make one covalent bond to the combination that goes like A1G, 3 bonds to the 3 combinations with symmetry T1U, and 2 bonds with the EG combination of S states. Okay, so this is what happens. And as I said, this is a simpler situation in which I considered s orbitals in each of the fluorine atoms. But in the problem set, you're going to consider the real thing, which is considering p orbitals. And it's going to get a little bit more complicated, but the idea is the idea when you have p orbitals, we have discussed this last time already, instead of starting from the equivalence atom site characters, you initially make the direct product of that with the vector representation, with the T1, in this case is T1U representation, okay? And then you start from that. That's how we would deal with p combinations of p states. Okay, we're gonna see more of that in a minute, and this is an interesting analysis to make when you have to consider the different types of bonds that you can make in a molecule or in a solid, specifically when you have to distinguish between sigma and pi bonds. So this is a brief review of sigma and pi bonds. For instance, when you have two neighboring atoms and one s electron and one s orbital in each of them, this makes what we call the sigma s bond. You can also make a sigma bond when you have one s atom and one s orbital and one p orbital oriented in the same direction along the bond, right? And this is a sigma sp bond. You can make a sigma pp bond when you have two p electrons like this, and you can make pi bonds. These are two different types of pi bonds when you have p orbitals which are perpendicular to the bond. Okay. Of course, p states. These are examples of p states. They are not as stable as the sigma states. The bonding from pi states is weaker, but nevertheless they are very important too. So here in this section we're going to learn how we can, from group theory, understand and distinguish the symmetries of sigma and pi states. Okay, so that's the idea, how to find separate representation of sigma and pi molecular states. Okay, so the recipe is that what I have discussed already. So you make the direct product of equivalence representation and the vector representation, and then you try to separate in two parts. So you try to separate the vector representation in components. One component perpendicular to the bond and another component parallel to the bond. The sigma bonding representation will come from the component of the vector that is parallel to the bond, and the pi bond representations will come from subtracting the general vector, subtracting from the total vector representation this term, okay, the components from the sigma bonds. So this will give me the representations of molecular orbitals of pi bonding character. Okay, I think this will get more clear when I discuss some example, and let's do this again. This is a hypothetical molecule. Let's a carbon 4 cluster, 4 carbon atoms arranged in the D3H symmetry. So this doesn't exist in nature, I think. Oops. But So that's the idea. I have one central carbon atom, and it makes bonds with 3 neighboring carbon atoms that are located in the vertices of an equilateral triangle. Okay, so this has D3H symmetry. This is the character table of the D3H group right here. This is the character table of the D3H group, all the different symmetry operations and classes, all the different irreducible representations. And once again, as we always do, we start from the atom site or the equivalence representation. That's going to be useful to consider the linear combinations of the 3 carbon atoms that are located in the vertices of this triangle. All right, so okay, so for when I apply the identity, all 3 atoms are invariant. For sigma H, again, all 3 atoms are invariant. For C3, they all change, so this is 0, this is 0 here. For C2 prime, one of them remains unchanged, and the same for sigma V. So this is the atom site or equivalence representation, and you can see that I can decompose into a sum of E prime plus A1 prime, the totally symmetric representation. Okay. So how do we do this? So we're going to do this in a very detailed way and in several steps. Okay, the first step before the first step, that what we have to do what we just did to construct the equivalence representation and decompose it into irreducible representations of the group. The second step, let's see the C orbitals from carbon atoms. Carbon has the S orbitals from carbon atoms. Carbon has S and P orbitals. Let's start with the S orbitals. And this is the same as we have seen many times already. So for S orbitals, the different combinations that I can make are essentially the same as the decomposition of the atom site representation. So I can make A1 prime and E prime representations, and this is we have seen many times already. The A1 prime is the totally symmetric sum, and the E prime has 2 partners when I introduce phase factors of omega and omega square, omega being e to the I 2 pi over 3. Okay, so these are the different combination of S orbitals. How about the P orbitals from corner carbon atoms now? So for P orbitals, as we have discussed, I have to make the direct product between the equivalence representation and the vector representation. So the representation for P orbitals, I can call it gamma P, is going to be the direct product between the equivalence representation and the vector. So, but what is the vector representation? Then I have to go back here at the character table and see where is the XYZ components of the vector. And I see here that the Z component is A2 double prime, and the XY component is a two-fold degenerate representation, E prime. Okay? So go back here. So this is the direct product between the atom sites representation A1 prime plus E prime with the vector representation, which I have just verified that it's A2 double prime plus E prime. Okay. All right. So, and I start already noticing that this comes from the Z coordinate. So if I think about p orbitals, this will be related to the pz orbital, and this will be related to the px py orbitals. Okay, it's important to keep that in mind. Okay, now I make the direct product. Let's make the direct product between A2 double prime and the atom site representation. So I'm going to skip the calculation, and I'm just going to tell you that this is equal to A2 double prime plus E prime. You can verify that. So this is coming from PZ again. And when I make the direct product of E prime with the equivalence representation, and after decomposing it, what I get is A1 prime plus A2 prime plus twice E prime. Okay, so this should come from PXPY. So these are the different combinations of p orbitals from the corner carbon atoms. Now I have to start thinking about how I can separate them between sigma and pi. And I know that Pz is always pi, right, in a planar molecule. So this should be in the end related to pi. But Px and Py, I can make both sigma and pi linear combinations. So this is sigma plus pi, and I have to figure out which is which. Okay. All right. So this is the second step. Now the third step is to consider this s and p orbitals from the central carbon atoms, and how can I make bonds to the corner carbon atoms. So the central carbon atom, once again, I have to see under the D3H crystal field how the S and P states decompose. So this is the result. The S state, L equals to 0, is A1 prime, and the P state, it's a decomposition of A2 double prime plus E prime. Okay, it's actually the same as the vector decomposition. Okay, so the central carbon atoms, if I use only S and P electrons, they can make molecular orbitals of those symmetries by making bonds with the corner carbon atoms. Okay. Finally, the fourth step is finding the sigma p orbitals. So in the second step, I found all the p orbitals for that I can make from the corner carbon atoms, and these are all of them. So now I have to figure out which one is sigma and which one is pi. So I do that by looking at the sigma atoms, and then if I figure out which are the sigma irreducible representations, I can subtract this. I can subtract from this the sigma part, and the remaining part is going to be the pi linear combinations. Okay, that's my strategy. Okay. So what I want to do now is to find the sigma p orbitals from the corner carbon atoms, these orbitals, by definition, they are directed towards the central carbon atom. So for this reason, they should transform like s orbitals. So it's easy to visualize when I draw them. So these are the different combinations of p orbitals that are sigma-like. They point in the direction of the center. And if you consider these three different orbitals, you can notice that they have precisely the same symmetry properties as the s orbitals in the carbon. Okay, they transform according to the same irreducible representations. So I can make a totally symmetric A1 prime representation combination by summing the three, and I can make two counterclockwise and clockwise rotation using the phase factors omega and omega square. And I hope you notice that this is it has to be exactly the same as the S combination. So this is the S combination, A1 prime plus E prime. Okay. So what I to find the pi representations, what I do is just subtract the sigma from the total. So what I do now is to find the representations for p pi. It's just going to be the representation for p, total p, minus this representation p sigma. Okay. And again, just writing again what I just wrote in the previous slide, this is what is the total representation for p orbitals. This was A2 double prime plus E double prime, and this comes from PZ pi plus A1 prime plus A2 prime A2 prime plus twice E prime, and this was coming from Px Py, and this has sigma plus pi on it. And now I subtract the sigma part. This is the sigma representations. So minus A1 prime minus E prime. Okay. And the result is A2 double prime plus E double prime. This is a PZ pi plus A2 prime plus E prime. And this should be then Px Py sigma. Okay? Sorry, pi. I subtracted the sigma. So I hope this is clear. And let's see again a picture of how this should look like, the pi bonding. The pi PZ, it's kind of trivial. What's interesting is to see how the Px Py pi looks like. You see that differently from the sigma orbitals, they are actually normal. They are normal to the direction going from the corner atoms to the center atoms. Okay, so this is the A2' combination, and when I add some phases, this should give me the E' combination of p orbitals that give me sigma bonding. Okay, another interesting thing is to notice that if you look at these representations, A double prime, E double prime, you can see that they are both odd under sigma H reflection. And this is how PZ orbital should look like, right? Because a PZ orbital is positive above the plane and negative below the plane. So it's odd under sigma H reflection. And this is the opposite as these guys. These guys are even under sigma H. So A2' and E' should be even under sigma H. A2 double prime. So the double primes should be odd and the primes should be even. And let's check if that's the case. If I look at the character table, and that's precisely the double primes are odd under sigma H, negative character, and the primes E' and A2' are even under sigma H. So this is making sense. You are going to explore some other examples in the problem set. And this is the end of this lecture. And this is the next problem set. It has only 2 problems, and it's due only on next Wednesday. Next Wednesday, not this Wednesday, next week's Wednesday, April 29. Okay? Thank you.